Good afternoon, everyone, and welcome to this joint EOL seminar with CGD, Climate and Global Dynamics Lab, and M-Cubed, Mesoscale and Microscale Meteorology Lab. Our speaker's seminar today crosses the research domains of all three NCAR labs. I am pleased to introduce Dr. Minghui Diao, who is an associate professor at the Department of Meteorology and Climate Science at San Jose State University in California. Dr. Diao received her PhD at the Department of Civil and Environmental Engineering at Princeton University. She is an NCAR ASP postdoc at EOL's Research Aviation Facility, working with Jürgen Jensen and collaborators at M-Cubed and ACOM, where she focused on airborne in situ measurements of water vapor, ice crystals, and aerosols. She has participated in a number of NSF field campaigns that some of you may be familiar with, such as Hippo, Orcus, and Socrates. Recently, Minghui was awarded the Early Career Investigator Award at San Jose State University, where her research interests are in the realm of aerosols, clouds, and climate modeling. And this segues nicely to her seminar topic, which covers these three atmospheric fields. It is entitled Ice and Mixed Phase Cloud Microphysical Properties and Aerosols Indirect Effects based on Multiscale Observations and Climate Model Simulations. We are using Slido to post questions, which you can type in at any time during the seminar. The Slido window is located below this presentation screen. Do not panic if you do not see your question pop up immediately, because we archive all questions until the end of the speaker's seminar presentation, where they will be revealed during the Q&A portion of the talk. Dr. Minghui Diao, we welcome you, and the virtual stage is now yours.
Thank you very much, Jackie, and thank you all for being able to attend this seminar, especially after this devastating weekend wildfire very close to the Mesa Lab. I hope all of you are safe and well. So for today, my seminar actually tried to bridge the gap between multi-scale observations and climate model simulations. So I look forward to hearing your questions at the end of my talk. And first, I want to thank all my group members for doing most of the analysis work, including my postdoc, Neil Desai, my current student, Qingyang Yang, Tyler Barron, Floor, Vanessa, Matthew, Derek No, and Dao Wang. I also have former students who conducted a large amount of the work shown in the paper publication today. And I want to thank my NCAR collaborator. I have collaborated with many of you in the past, but recently I've been collaborating with Adriana and Christina and Andrew Gettleman. So at the end, I want to thank all the hard work from the field campaign teams, such as the NSF and DOE field science team. So now let's first take a look at this big science question about cloud perturbation. I actually grabbed a few very recently published figure from the IPCC AR6. This was published just in February 2022. The first figure on the left, top left, we can see if you combine several anthropogenic greenhouse gases, their radiative forcing will add up to about 3.8 watt per meter square. And these are the gases we're talking about. If you compare that number to the global cloud net forcing, which is a negative 20 watt per meter square, you know, just about 20% change of the global cloud radiative forcing could either cancel or double all of the anthropogenic greenhouse gas that we're talking about. And unfortunately, what I circle out here in the purple color is actually where, is where the aerosol cloud interaction is being listed. You can see large uncertainty still associated with this. Another figure on the bottom is the feedbacks in the climate system. Here I highlight this feedback called the cloud feedback. It is actually one of the largest uncertainties in all of the climate feedbacks, much larger than surface albedo feedback, et cetera, for their uncertainty. So this is where we're at, still at the current status for a lot of uncertainty in how clouds will respond in a future climate. with a little more zoomed in look at the Southern Ocean and Antarctic clouds, this is a hot topic in the last few years. On the top panel, I show the satellite view of the cloud radiative forcing of 3 types of cloud thermodynamic phases. So depending on if you're liquid cloud, ice cloud, or mixed phase cloud, you can have very, very different cloud radiative forcing at the top of atmosphere. And that is why it is very critical to represent these phases correctly. And here on the second row is a figure of the temperature curtain at various latitudes. In the yellow is what the satellite saw. There's a 90% transition into the ice phase from the liquid phase. And versus the green thick line is the model simulation shows where the transition should happen. So from the CAM5 model or the CM3 model, obviously this transition happened at a much higher temperature. So they allow too much ice to happen too early. And here's the question for observationalists like me. How can we actually conduct meaningful comparisons, such as scale-aware, definition-aware comparison between high-resolution in situ observation and chord-scale simulation? And if we do such comparison, can we find any typical model biases for representing these clouds? And what are the lessons we can learn for future development of cloud parameterization? Now, a little background of what I used to do. Just like Jackie said, I had a long history of working with many of the scientists at NCAR EOL Research Aviation Facility. Since I was a graduate student, I was involved in many field campaigns early on, like Startle 8 or HAPO, and recently the Socrates. And now, even though I'm not in the field, I'm still trying to contribute to the laboratory calibration of the VCSEL hygrometer. So many of you from the modeling community, you may actually have this question: why do we put so much resources, so much money and time to do in situ measurement, which may only happen in a short amount of time, only cover a small scale geographical locations compared with satellite data? So here's a study that may help you to answer some of that question. I did a validation of a satellite product called the NASA AIRS water vapor and temperature product. And you can see this is the swath from the satellite data. And this is the co-located satellite data with the aircraft measurement. And we found from the satellite data, there's about 20 to 40% difference for water vapor mixing ratio. And then there's a 1 to 2 Kelvin difference in temperature from the surface to the UTLS. And that may not seem to be a very large differences, but when you want to study mixed phase cloud, when the liquid saturation and ice saturation would only differ from each other by a few percentage to 10, maybe 30% of RH relative humidity, then it could mean totally different if you're a liquid cloud or ice cloud, depending on what relative humidity you're observing. So that's why it is crucial that we have such high resolution, accurate observation. Coming back to the fundamentals of providing accurate measurement, I have been collaborating with many NCAR EOL scientists to support this water vapor hygrometer called the VCSEL hygrometer. In 2018 and 2016, my group actually were fortunate enough to be supported by the NCAR ASP faculty fellowship to spend the summer at NCAR. We were able to use the foothill environmental chamber to do the calibration. So the take-home message is when you fly in an aircraft to sample the real atmosphere, we need to be able to mimic the condition of atmosphere back in the laboratory. We need to have a combination of pressure, temperature, water vapor in order to make sure our measurement is really as good as it can be. Here is a cartoon view of how the foothill chamber was set up. And this is when I did the post-campaign calibration for the VCSEL hygrometer back in 2018, supporting the ORCAS and Socrates measurement. And because of this support from NCAR, I was able to provide a PI data for the water vapor. And recently there is a version 2 data for the Socrates that's hosted at the EOL website. And what we did is we put part of the optical system of VCSEL inside the chamber. And then we have the laser box, all the electronics outside. So inside the chamber, we can actually go as low as -70 degrees C and go up and down, do many weeks of calibration. And the result shows it is really helpful. In the past, when I was a graduate student at Princeton, we have the 2013 calibration. It used to peak at 96% for RH liquid. After my calibration, it now peaks at 101%, much physically sound for measuring liquid cloud. For the RH ice, in ice cloud, it used to peak around 106%, now is peaking at 99%. And this is definitely helping us to understand the difference between ice and liquid, and also understanding the transition between ice and liquid. So part one of my talk will focus on ice, liquid, and Makeshift clouds over Southern Ocean and Antarctica. And this is the temperature range I will only cover between 0 and -40 degrees Celsius. So to start this part, I want to quickly mention what is the definition of Makeshift cloud based on AMS glossary. It just says if you contain both supercooled liquid water and ice crystal, then we call this a liquid phase, a Makeshift cloud. However, this definition is a little bit loose because depending on what is the scale of your observation, what is the technique, what is the instrument you're using to make such measurement, or what is the model simulation you're trying to simulate in Makeshift cloud, you can come up with slightly different definition. You see from the observation point of view, these are some 2DC probe images where you can see ice phase clearly with ice crystals and some mixed phase with possibly frozen droplets and embedded with some dendrites. And then we also have some columns of ice. So it's very heterogeneous at a high resolution. But how can we use such heterogeneous observation to compare with hundreds of kilometer scale model simulation, such as climate model? Here's the overview of a few field campaigns that we have been using in the last few years. Part of HAPO is shown in red. We have Orcus, we also have Socrates. So the goal is that we will develop methods that can distinguish hydrometeors from the observation. And then using that, we can define statistical distributions based on a large composite data set. And from the statistical robust distribution, we can use it to evaluate the climate model. A quick overview of some of the key instrumentations I will talk about. For the cloud probes on the Gulfstream 5 research aircraft, we have cloud droplet probe, CDP, and fast 2DC probe. We also have the 2DS probe for Socrates, but not for other campaigns. We also verify our cloud phase based on RICE, icing indicator, or King hot air probe, and the VCSEL hygrometer combined with temperature can provide RH measurement with uncertainty about 6 to 7%. So these are the images of where you can see VCSEL sitting on the top, and all the other cloud probes are under the wing. We developed this technique back in 2019, publishing our paper in journal Climate. So back then, our first obstacle of using in situ aircraft data is how can we define what is a liquid phase segment, what is mixed or ice phase. We use CDP and 2DC or 2DS based on their number concentration, based on their mass concentration. We develop this diagram. So from this, we can define what is large aerosol, what is liquid, and what is ice. And combining the two probes, we can get the total liquid water content and the total ice water content. And from there, we can know what is the dominant hydrometeor in a segment, such as hundreds of meters to hundreds of kilometers. So a quick demonstration in a case study. This is from Orcus, which is located at Punta Arenas, Chile. So the Orcus field campaign research flight 17, we plotted on the top two rows, what are the real observations, in situ observation, and on the bottom, what is the co-located nudged Cam 5 simulation. We can see there are times that rise indicators show a ramping up of supercooled liquid water, and that is a very well correlated with where we also define either liquid phase or mixed phase. In the red is liquid, in the green is mixed. And we can verify this using the images of different cloud probes. However, back in 2019, the CAM5 model had trouble of capturing a lot of the supercooled liquid water. As you can see, for this entire segment, CAM5 thinks it is ice. And moving on from a case study to a statistical distribution, we have to develop a method that really can be scale-aware, definition-aware comparison. I borrowed this key term, scale-aware, definition-aware, from the study of Jen Kay, because she uses this term to define a satellite comparison to model. And I find this would be really critical to develop comparison method between in situ observation as well. So what we do is aircraft observation, they come through usually 1 Hertz data that is also, often 100 meter to 200 meter scale. But we can do spatial averaging to get 20 to 50 kilometer scale from the surface to the UTLS. That becomes a lot more comparable to the climate model in the high latitude. And second, we can use same definition to define cloud phase. We use a mass fraction of liquid. If the liquid mass fraction is less than 0.1, we call this ice phase. Otherwise, there is mixed phase or liquid phase. And please note, this is actually very different from many previous observation studies use that previous AMS glossary method to say, as long as you find liquid and ice, then that would be mixed phase. Because if we follow that method to define climate model grid, most likely some liquid and some ice will appear at a 100 kilometer gray box scale in a climate model. So we cannot do that. That is a vivid example why we need to develop new method to define these things before we compare with climate model. And for the quantities, we use great mean quantity and derive that from the observation. Now below is what we found. We averaged the Socrates observation from 1 second to 580 seconds. That is actually about 100 kilometer scale. Now, if we compare this coarse observation being averaged with 3 models, CAM6, CAM5, and the E3SM EAM1, we found CAM6 actually shows the most similar cloud phase frequency distribution. And that's really good news, because in the past, CAM5 would not be able to capture any supercooled liquid water below minus 10 degrees Celsius. In addition, we were also able to see some interesting feature of CAM6. There is a transition between liquid and ice. The crossing point here happens about minus 15, and in observation, it actually happened about minus 20. So these are some of the ways we can evaluate how it is presenting different cloud phases. We can also directly evaluate the mass concentration, which is liquid water content and ice water content. And before I go into this slide, I want to first tell you, in the past few years, when we use satellite data to evaluate AMIC5 model, we often find there's too little liquid water content or too little supercooled liquid water over the Southern Ocean. Is that still the case when we compare with the in situ observation? So we plotted liquid water content versus temperature in the first row, and second row is ice water content versus temperature. Then glaciation ratio or ice mass fraction is on the third row, and the glaciation ratio for only mixed phase cloud is on the last row. Some of the key messages we found is for temperature between 0 and minus 20, CAM6 and E3SM actually show much significant improvement compared with CAM5, which used to totally severely underestimate supercooled liquid water. But there is too high of a liquid water content now at temperature lower than minus 20, seen in both E3SM and CAM6. And vice versa, there's actually too little ice water content now in these two models. And how this will actually manifest the effect on other metrics, such as equilibrium, climate sensitivity, is something I am really interested to know. If we use to sense there's too much ice and too little liquid water, and now it's becoming the opposite, how will that actually affect our estimation of temperature increase in the next 100 years? And this study, actually, you can find the detail in my student Qing Yang, her recently publication over for the Socrates campaign in GGR. So another thing that Qing has been doing is to do a hemispheric comparison. Now we have many field campaigns, some in the northern, some in the southern hemisphere. How different are they? We have Socrates orcas as part of Hippo representing the southern hemisphere. Now the second row, we have DOE, MPACE, ESTAC, and the Hippo, NSF Hippo representing the northern hemisphere. In general, we found if you combine the northern and southern hemisphere, there is actually higher occurrence frequency of liquid phase in the supercool phase found in the southern hemisphere compared with the northern hemisphere. And whether or not this is related to the aerosol indirect effect is something that we want to further investigate. Now let's shift gear and not only focusing on aircraft data, but also take a look at the shape-based field campaign from Marcus campaign. This is a DOE campaign, took place over the Southern Ocean in 2017 to 2018. And we have many instruments on board, such as microwave radiometer, there's a W-band cloud radar, macropulse LiDAR. All of these will help us to derive the cloud phases in the remote sensing data. So this is the work actually carried out by my postdoc researcher, Dr. Neil Desai. Neil has been trying to optimize a method that was previously used by Matt Schuppe in 2007. But that method actually was not optimized for Marcus campaign, nor was it actually optimized for the MPL. That was used in the HSRL, a totally different LiDAR. So Neil has been changing this algorithm based on what the MPL actually would perform the best. So here's the reflectivity, LDR, Doppler velocity, and we can use that previous chart to identify where's the rain, where's ice, drizzle, snow, etc. This is 1 day of case study at a higher resolution using the shape-based observation. And now we can also use this to compare with the climate model. So on the top right is what you just saw. This is observation data. On the bottom left is what we spatially averaged the observation into the climate model grayscale. And we remove the difference between snow and ice. We call all of that ice phase. We also put the rain and drizzle into the liquid phase. So that's why you start to see more red here, because drizzle will become the liquid phase now. And this on the right-hand side is the DOE E3SM model being nudged towards the reanalysis data. So the good news is the capturing of the cloud top and cloud base seems to be very realistic in the E3SM model. But the bad news is you can see the cloud phase are very different looking. Seems like there are vertical structure missing in the E3SM model, while the stratification is more detailed in the observation. And from another way to look at this, similar to what we did before, is moving on from a case study to a statistical distribution. Now, what we had in the first plot on the left is a high frequency observation. In the middle is the spatially averaged observation. On the right-hand side is the E3SM nudge simulation. Again, we saw much higher mixed phase frequency in E3SM. And if you still remember, just a few slides ago, I showed you my paper by my student Qing Yang 2020. She found similar feature in E3SM, too much mixed phase cloud over the domain of Socrates campaign. So 2 different campaigns, 2 different location and year over Southern Ocean showed very consistent model biases. And that is what I want to point out. We'll go into the direction, how can we provide more robust comparison? I will mention that in the end. So moving on to the Antarctic observation, AWARE field campaign is one of the first study, I think it's the first study since 1957 International Geophysical Year that DOE and NSF put a collaborative effort to conduct more than a year of observation at the McMurdo Station, Antarctica. So this data set helped us a lot to understand cloud fraction, cloud phase from the McMurdo Station, and how do climate models represent these over Antarctica. The observation instrument we use has the cloud radar, CASR, and we also have the HSRL, which is a high spectral resolution LiDAR. Now on the top row is the derived cloud phase from the radar and LiDAR combined. You can see very thin supercooled liquid water top, and this is a very typical feature that we saw at McMurdo. These thin supercooled liquid tops are only about 100 to 200 meters thick, and yet sometimes the climate model would exaggerate it into a much deeper liquid phase layer. So again, the good news is CAM6 model plotted here, notched towards the reanalysis data, was able to capture the location, the onset time of this cloud structure. But sometimes there's overestimation of cloud fraction, or there's underestimation. They are highly correlated with the biases seen in the thermodynamic condition, such as relative humidity condition here. The model overestimate RH liquid by 60%. So no doubt they actually overestimate cloud existence as well. Now, what is the overall result from the entire year of AWARE campaign? We saw observation in the red and model in the black line. There's actually overestimation of cloud fraction above 3 kilometers, but underestimation of cloud fraction below 3 kilometers by the model. More interestingly, if we look at the cloud phase frequency, we want to know if the model gets the ice and liquid right. We saw when we had low cloud fraction, less than 0.3, there's actually, the blue color is the observation, there's actually overestimation of ice phase. But when you have high cloud fraction, when you have continuous extensive stratiform cloud, low-level stratiform cloud, there's actually too little ice phase in the model. So there's a dependency on the type of cloud for how the cloud phase bias will play out. We also find out this interesting correlation, how the relative humidity bias play a major role in the biases of cloud fraction and cloud phase. And this paper was led by my undergrad student, Jackson Eve, and also my grad student, Tyler Barron. We published this last year as well. Feel free to take a look. So now what Tyler has been doing recently is to link the cloud biases to the radiation biases. We know that models sometimes overestimate or underestimate different phases of cloud, but how does that matter for short wave or long wave radiation? This is a case study that Tyler picked out. We have this extensive low-level stratiform cloud, again, with some thin liquid cloud top. Second row is the E3SM model, and third row is a CAM6 model. Too much red, meaning too much liquid phase, too much green, meaning too much mixed phase. And these are all correlated with the radiation biases. You see the blue line is the, I believe is the CAM6 model, and the black line is the observation. So what we can do, what we can see here, the CAM6 model actually would have too little solar radiation coming in because these liquid phase, fake liquid phase blocked out or reflected back too much of the shortwave radiation. And moving on to a statistical analysis, again, this is AWARE data from January to December at McMurdo. We have observed net shortwave at surface, and we have the BOE model, EMV1. So we see a correlation between the shortwave biases and the cloud fraction biases. And such correlation is even stronger for, I just switched the slide because I want to focus on this CAM6 result. So this correlation is a lot stronger compared with the correlation on the third row, because the second row is the cloud fraction biases only at the lowest altitude from 0 to 3 kilometers. And the last row, third row, is the higher altitude cloud fraction biases between 3 and 10 kilometers. We can see this is a tighter correlation with higher R² value. And that just shows that the low level cloud actually plays a more dominant role for controlling the short wave and long wave radiation biases. So part 2, now just checking my time, make sure I have enough time for my part 2. This will actually switch gear to focus on the aerosol indirect effects. So far, we haven't talked about anything about Cirrus Cloud, and I want to say a little bit why we also care about the Cirrus Cloud, which is so high in the altitude, and temperature-wise, we only analyze temperature below equal to -40 degrees Celsius. So in a comparison from this diagram, let's say if in a model we thought there is Cirrus Cloud, but these are actually fake Cirrus Cloud, but in reality, we should have clear sky supersaturation called the ice supersaturation, where relative humidity with respect to ice is greater than 100%. How would this make a difference? So the model would think that you should block some of the short wave radiation and also trap the outgoing long wave radiation. But in reality, if you're a clear sky, it does not reflect short wave radiation by the cloud because the cloud was not there, and you still trap the outgoing long wave radiation by other greenhouse gases. And the difference between the two, based on one of the studies we did in 2016, could lead to average biases of 2.5 watt per meter squared in a local bias whenever you misrepresent the clear sky as fake Cirrus Cloud. And this is a pretty large local biases. So how can we actually evaluate the model for this formation of Cirrus Cloud, and how can we understand the effect from aerosols? We use this large composite NSF field campaign, basically from 7 field campaign I talked about in the beginning as well. It covers both northern and southern hemisphere. And this is the figure that is from my former student, Ryan Petnot, who is now at Colorado State University. In 2020, we published this paper in GRL, focusing on the linear relationship between log scale ice water content and log scale aerosol number concentration for large aerosol. And by large aerosol, I mean greater than 500 nanometer. We conduct linear regression at different temperature. So if you see the temperature being black, that's all temperature. The blue meaning is very cold temperature, and the red is closer to -40. We found that there is higher slope, meaning larger aerosol indirect effect for the large aerosol NA500 at higher temperature. So basically, large aerosol are more effective for increasing the ice water content of Cirrus Cloud when you are close to -40 degrees Celsius. And this is actually very interesting because it suggests heterogeneous nucleation is playing a critical role at these slightly warmer temperature. On the other hand, the smaller aerosol greater than 100 nanometer are found to have more effective aerosol indirect effect at lower temperature, closer to -70 degrees Celsius. That indicates homogeneous nucleation. On the bottom, I pulled some of the number of this slope based on a series of previously published modeling work. And you can see the slope value from their study, their study is 0.1 to 0.3. Well, the study Ryan and I did showed it's about 0.2 to 0.4. So we know there's even stronger aerosol indirect effect found from the in situ aircraft data. But how much this will mean for global Cirrus Cloud biases is something we haven't investigated yet. And from a latitudinal band perspective, if we look at the tropics, mid-latitude, and polar region, the blue color is the 1 Hertz data, and the black color is probably what you want to focus on, is the averaged observation into 100 kilometers. And the red color is a CAM6. We found that CAM6 in general simulate too many ice crystal, and all of them are too small. So their diameters are so small, and the ice crystal number concentration are too high in the model. In addition, for the hemispheric differences, in mid-latitude, for example, you see the black solid line representing northern hemisphere mid-latitude is much higher than the dashed black line representing the southern hemisphere mid-latitude. That bifurcation between the two shows how it is likely that the difference between northern and southern hemisphere, either land-ocean differences or aerosol concentration differences, could lead to Cirrus Cloud property differences. But that is not really captured by the model. You see the solid red or the dashed red line are pretty close to each other. So again, this seems to indicate that for future development of parameterization, should we focus more on the aerosol indirect effect, and how can we, which part of the parameterization should we add more aerosol indirect effect, and something to be considered. Now, moving on to this slide is actually a curtain plot with temperature on the y-axis and aerosol number concentration on the x-axis. The left two columns are using large aerosol on the x-axis. The right two columns use small aerosols on the x-axis. And what we saw here, the observation has an interesting gradient of color, more red at higher aerosol concentration, indicating higher ice water content, higher ice crystal number concentration, and even slightly higher diameter when the aerosol concentration is higher. And the cloud fraction also has a significant response to higher aerosol concentration. But all of this, if you look at the CAM6 notch simulation, there is only a slight increase in NI, but the increase in ice water content or diameters are much lower than what the observations have found. So again, just from another perspective, how do we capture these observed aerosol indirect effect, and how do we represent in the model is something to be considered next step. And this slide is what is done on the Makeshift Cloud. So the slides before only focused on Cirrus Cloud at temperature below equal to -40. This one is different. This focuses on ice and Makeshift Cloud between 0 and -40 degrees Celsius. So what Chin has done is comparing different scales of observation, again, with CAM6 and E3SM model. We found the observations show increasing liquid water content and liquid concentration, and that is not shown clearly in the model. But besides the liquid phase, the ice phase is probably even more severely underestimated for aerosol indirect effect, which I will demonstrate in the linear regression. Is more easier to see this. So if you look at the bottom two rows, this is a linear regression between liquid water content, the third row, and ice water content, the fourth row, versus large aerosol number concentration, NA500. Observations show positive trend, no doubt, but CAM6 have either no trend in liquid water content or even a decrease in trend for ice water content. E3SM, same case, either very little response to aerosol or there's a decrease in trend. And this is actually the response to large aerosols. The response to small aerosols are also not perfectly matching the observation. There is a weak positive correlation in the observation, but that is, so that good news, it is partly captured by CAM6 for the liquid phase. So yeah, good then there's a 2-mid effect on the liquid phase for the small aerosols, but not so much for the ice water content, and not so much for the E3SM model in either ice or liquid phase. Now I will just talk about a few slides for ongoing work. My new graduate student, Derek No, he's leading this work in aerosol indirect effects on convective cirrus and in situ cirrus using a combined data set between NASA and NSF. We are including new data set because a lot of the NSF campaigns are not focusing on convection. Maybe exception is the DC3, but a lot of NASA campaign actually target on convection. So we conducted some preliminary analysis, and the good news is we saw similar positive trend in terms of ice water content, ice crystal number concentration, mean diameter with respect to large aerosol. But we also see some discrepancies with NSF data. And we want to figure out how the two type of cirrus generated convectively or in situ, how they respond differently to aerosol concentration and different composition of aerosol. And my other graduate student, Vanessa, so Vanessa Matthew, she's been looking at evolution of Cirrus Cloud. To give you a quick look, this is just how Cirrus Cloud would evolve from a lot of supersaturation, but a little bit ice crystal to the part of a lot of ice crystal, little supersaturation, and eventually to the sedimenting phase. You use up all the ice supersaturation and you have no more RHI above 100% and you're only ice crystal. And from then on, it's only gonna be sublimation. So this is a interesting transition in view from the aircraft data. We look at 1 Hz or 430 seconds. We can also compare with CAM6. What is interesting here is plotted on the x-axis is the sigma W. For the observation is the standard deviation calculated for different pockets of observation data. For the model, we use the W sub I variable from the model. And we saw a very low W sub I in the climate model. This is not a, I wanna say this is a variable mainly to initiate RHI variability at the subgrid scale. But question is how can we change this variable or use other ways to represent the subgrid variability? Maybe that will help to improve the simulation of Cirrus Cloud or the initiation of ice nucleation. That is all active questions that yet to be answered. So one more ongoing work by my student Qing'an Yang. We got a little funding from SGSU research development just to kick off on this topic. I also talked with several other people at NCAR about this. We want to develop an aircraft instrument simulator specifically for different type of global climate model. So here I listed what is the current status when we currently compare aircraft campaign and global climate model. Usually we're limited to one campaign, one instrument, one aircraft platform. And usually we're limited by the funding. If we're funded by DOE, we will use DOE field campaigns. If we're funded by NSF, use the NSF field campaign. And it is very difficult also to break the boundary between different instrumentation, different aircraft platform, different geographical location, and then combine them into a merged data set that can be used to assess a larger scale global climate model simulation. So in my previous work, I already demonstrated to you, we developed some methods, but to develop a systematic method that we can reduce the barrier from modeling community to use the in situ aircraft data is something I would like to put more time on. So the goal of this instrument simulator is we will document the statistical robustness and the uncertainty of using in situ aircraft data. What kind of cloud microphysical properties are actually resistant to different sampling strategy, different days, different geographical locations? What kind of statistical distribution are very sensitive to the spatial scale, and you should be cautious when you use high resolution data? And how can we provide a software where the modeling group only need to download the software and provide one output from the model, and they can just automatically get a quick evaluation result from the software? I would love to hear the feedback from the community on this topic, because I think this is a sorely needed task, and it would really help to bridge the gap between high resolution observation and a model. So in conclusion, we developed a series method to conduct scale-aware, definition-aware comparison between GCF simulation and high-resolution observation, including airborne, shipborne, and ground-based observation. we found different types of model biases of cloud fraction, cloud phase, cloud microphysical properties. And we found a lot of them are largely correlated with biases in thermodynamic, dynamic conditions, and especially water vapor mixing ratio biases. Now, the third bullet point is quantifying aerosol indirect effects requires isolation of many other factors. Even though I didn't go into detail about that, I want to say in the GRL paper that we published in 2020, we realized if you do not isolate these other factors before you quantify aerosol indirect effect, you could even get completely opposite result, because aerosol indirect effect is considered to be more secondary compared with the other effects are just more dominant. And climate models underestimate aerosol indirect effects on ice and Makeshift Cloud. We've seen that through both Cirrus Cloud studies and Makeshift Cloud studies. And particularly, we see an underestimation of aerosol indirect effect for the ice phase. And for the 2 points, 2 and 3, we have found some common problems in several GCM simulations over various geographical locations. And one of my questions mentioned earlier is if we have new findings from the in situ observation that was not pointed out before by satellite data, what will this indicate for our future climate projection? So I also took some screenshot of my current team member yesterday when we do the Zoom call, because I'm still on sabbatical. We're still doing this virtual interaction. And in 2019, I was very lucky before COVID started. I brought several students with me to NCAR. And I really hope, when everything is back to normal, I'll be able to visit NCAR again. So this last slide, I put here my acknowledgement to my 2 NSF grant, DOE ASR grant, a NASA Roses grant, and several other support from Lawrence Zimmerman Lab and ASP Faculty Fellowship and SGSU Award. And on the right-hand side are some of our recent publications. And I would love to take your questions. Thank you so much for your attention.
Great. Well, thank you, Minghui, for your talk on covering a multitude of aspects of cloud microphysics and aerosol indirect effects using observations and climate models. We have time for questions or comments. May I remind the audience to please use the Slido interface, which is below this presentation screen. You scroll down to ask your question. I'm hoping, and I'm sure that there's some fellow modelers and observationalists out there in the audience who have some questions or comments. Minghui, you presented a lot of motivation and information. Are you planning any field campaigns to bring the VC SEL hygrometer on the aircraft?
That's a great question, Jackie. I currently am not involved in a field campaign, but that is something I would love to do and hear what is the need from the community. And I know there are some new interests in the Arctic measurement. A few years ago, I was involved in a field proposal. Unfortunately, it was not chosen to make Arctic measurement, but that is something I think I would love to do.
Quiet group.
Yeah, probably had too much information. I just
if there's such a thing. It's interesting to see how you interpret the order and pattern of seemingly chaotic observations of cloud fraction and cloud phase and the aerosol indirect effects. It seems that models still have a ways to go to match the observation systems that you've been using. You definitely highlighted the deficits, but maybe I missed this, but what do the models actually get right?
Yeah, this is a great point. So a lot of times we saw that the location and the onset time of clouds are much more improved compared with the earlier model. And we also saw several models, E3SM, DOE model, and the CAN model were able to get the cloud top and cloud thickness right. I think we're just raising the bar higher, ask the model to get more and more sense right.
Mm-hmm. Right, so it's a work in progress, and we certainly need those evaluations to keep the modeling community on their toes.
Yes.
We have a question from Britt Stevens, and he asks, hi Minghui, nice talk. Any speculation on ways forward to improve the models?
Thank you, Britt. Yeah, really nice to see you again. And that's a great question. I think one of the things I really want to do is to bridge the gap between multi-type of observation. We usually rely on satellite data to evaluate the model, either for radiative forcing or for cloud phases. And I totally agree, because satellite data can provide large coverage and they have many years of data to provide longer record. But I also find it could be a little undesirable if we totally rely on one measurement technique to evaluate the model. So one thing I want to do is to use this aircraft simulator to be able to identify any systematic biases in the satellite way of evaluation. And that may go into many directions. It could be just cloud, it could be just aerosol, or it could be cloud aerosol interaction. And if I say, how to improve the model, I think there are several directions. It may actually make sense even more complicated. I know many modeling groups are focusing on regionally refined model simulation now. So it raises a new question: will the current parameterization still work when we have model gray box in a region at a few kilometer to 20 kilometer-ish? And that actually make an opportunity for us to say that may require more usage of the high resolution data to improve these parameterization. Either there are cloud microphysical, microphysics parameterization or aerosol parameterization. Thank you, Britt.
Thank you, Britt. We have a question from Greg Casana. I apologize if I don't pronounce your last name correct. He says, it seems that you show that one model simulates too much ice with large cloud fraction and too few with small cloud fraction. Did you get a chance to look at the mean top of the atmosphere shortwave bias related to this cloud phase biases? Thanks.
Yeah, Greg, this is a wonderful question. Yes, so for the first paper that we published on the AWARE data, we kind of just stopped at the evaluation of cloud itself. And my graduate student, Tyler Barron, he's been looking at the surface radiation comparison using the AWARE surface measurement, but also we can compare with the TOA, such as using Cirrus satellite data. So one thing, like I said, we do have some recent finding. We noticed that liquid water path is a strong controlling factor on the radiative biases, both at surface and TOA. But liquid water path would also be affected by cloud fraction biases. So it's like if you have too much cloud, but too little liquid water content, it could cancel out each other. And we're trying to find a way to quantify each of these factors, how they will influence the final radiative biases by controlling everything else. Yeah, thank you. This is definitely an ongoing direction.
Thank you for that question. We have a question from Lulin, who says, nice talk, Minghui. Do you have any plan to perform model observation comparisons and evaluations for cloud resolving models or even LES models? This may help bridge the gap between the observations and climate model simulations.
Yes, thank you, Lulin. Long time no see. Thanks for coming. And that's actually a really good point. And I can tell you, I'm very interested. Back when I was an ASP postdoc, I had the opportunity to collaborate with George Brown and Hugh Morrison at MCube. And George has the CM1 cloud resolving model. We conducted comparison between CM1 and one of the NSF field campaign called DC3. And we actually were able to identify something interesting, what the model can or cannot do. And actually, that's a really great point. I forgot to mention, not only observation have various scales, but model simulation have various scales. I know sometimes we can use high resolution model to test the parameterization if we want to insert them into coarser resolution model. So that is definitely a very interesting topic. I will be happy to talk with you more about that. Feel free to reach out to me.
Wonderful. Thank you for that question. We have a question from Jeff Stiff. He says, thank you for an excellent talk. If you were to design a large field campaign to address some of the remaining outstanding questions, what would you propose?
Wow, wonderful question, Jeff. I should know this, and actually asked my students to answer this question just yesterday. I said, if you guys plan for field campaigns, what would you like to do? Well, I would say, I think right now, since I mentioned, there are some gaps between different scales of observations or simulations. If we can plan the field campaign with that in mind and try to answer some of these fundamental questions, such as what kind of cloud microphysical properties are very sensitive to the spatial sampling scale? How are they sensitive to the location you sample, cloud top, mid-layer cloud, cloud bottom? And how will that change our evaluation of model? I know now we start to have many more modeling experts joining the field campaign, such as Socrates. But I think if we can keep that tradition and also keep in mind in the flight track design, how this will answer some of the fundamental ways to evaluate the model, that will be also helpful in addition to just, okay, we'll just evaluate this model at one time. And Arctic, sorry, Arctic, I think it would be really cool if we can sample Arctic.
Going from one pole to the other pole.
Yes.
Thank you for that question. We have a question from Hugh who says, great talk. Glad you emphasized the importance of scale, especially comparing models and observations. Any comment on smaller scale variability in stratiform mixed phase clouds below the scale observable by aircraft data, say less than 100 meters? Could this be important in understanding overall mixed phase cloud behavior?
Yes, Hugh, thanks for bringing this up. This has been a very important question. I remember right before COVID hit, I attended this workshop on a possible cloud chamber. And of course, at cloud chamber, we can control all the conditions and make even higher resolution observation. But just given the current instrumentation capability on G5, VCSEL can measure at 25 Hertz, and there is high resolution, high frequency temperature probe. We can use that as well. So yes, there is a possibility if these probes are calibrated at this high resolution, we could even measure relative humidity at much higher variability. And then we have other cloud probes that can see individual cloud particles. And if we want to go to the direction of understanding small pockets of ice crystal, how do they first form in a segment that used to be all supercooled liquid water? I think going into the higher resolution will be really critical to answer that kind of question. How does the first ice crystal form in mixed phase clouds? And after they form, how does vertical velocity or the variability of relative humidity support the longevity of mixed phase cloud? Is it through turbulence? Is it through circulation, in-cloud circulation? I know there are some theoretical dynamical possibility proposed in paper by Alexei Kolorev, but how do we verify that from aircraft observations? That would be really cool if we can do that.
Great. Well, thank you, Hugh. That was a great question and on a high note answer. So we are at the seminar hour. If you are interested in Dr. Minghui Diao's presentation and have further questions, want to reach out to her via email, which is provided on the seminar flyer. On behalf of EOL, CGD, and M-Cubed, I would like to thank Dr. Diao on her excellent presentation evaluating climate simulations of various aspects of cloud microphysics and aerosol indirect effects. Thank you, everyone, and have a good day.
Yes, thank you all. Take care. Have a good day.